Welcome to the next new video. A popular request on my last devlog was to cover manual memory management. I definitely did not bait you into this request by saying I cut out a minute-long rant. Dark Triad? Me? Impossible. For those of you who watched my math videos, you're probably already strapping in, because you, dear diehard viewer, know just how painfully fast I can go. So, manual memory management at breakneck speed. But before I give you whiplash, if you're not familiar with the basics of C and C++, say, if you don't know what I mean when I say malloc, you are going to be confused. I recommend checking out Beej's guides to C and C libraries, especially my beloved string library. C is not a hard language to learn, and compared to most other languages is extremely small and straightforward, which for demonstration purposes is perfect. Also, the link to the GitHub repo for all the source code for this project can be found in the description. Proficient manual memory management offers advantages other than the ever-celebrated cache locality. After all, the only way to truly ensure cache contiguity is to place your data back to back manually. And maybe this is just me, but once you become good at memory management, you achieve a truly Zen perspective on common memory issues. I'm not saying you'll stop forgetting to free your heap allocations, I'm saying you won't have to. So, to really put us in the proper mood, here's this famous email.
This sparked an interesting memory for me. I was once working with a customer who was producing onboard software for a missile. In my analysis of the code, I pointed out that they had a number of problems with storage leaks. Imagine my surprise when the customer's chief software engineer said, "Of course it leaks." He went on to point out that they had calculated the amount of memory the application would leak in the total possible flight time for the missile, and then doubled that number. They added this much additional memory to the hardware to support the leaks. Since the missile will explode when it hits its target or at the end of its flight, the ultimate in garbage collection is performed without programmer intervention.
This anecdote leads us into the first of two questions that define manual memory management.
Why are you freeing?
And this ties into why I'm using C for this video and why I like it so much. From my perspective, if a language has a garbage collector, it is immediately ruled out for manual memory management. I know C# lets you manually manage memory, but you're going to have a hard time. And you may think the smart pointers of C++ offer good memory management, but they really just stop you from leaking memory since they answer the question with, "but I do free." Likewise, Rust's boxes make the same mistakes as smart pointers, but with the added headaches of Rust's slow compilation time, having to implement copy again and again, so that way its ownership model doesn't free your variables from underneath you, and its borrow checker pill-pulling your code. But as you can probably tell, my dalliances with Rust left a poor taste in my mouth. And while I know Odin and Zig have allocators built in, that unfortunately rules them out for demonstrating how to manage memory, which, as I said at the start, is why the lion's share of this video is going to be in C. But first, we use C++ to demonstrate how to manage memory poorly. Say, for example, you want to use a quadtree to perform broad phase collision detection in a 2D game. I wrote out a simple quadtree class and visualizer with Realloc. I'm simulating dynamic collider density with a random number generator. If we look at my code for generating the quadtree, we can see it follows the classic RAII paradigm. If the quadtree's dimensions are above a minimum size and there's a detected overlap, then I simply add 4 new quadtrees, each a quarter of the size of the parent quadtree, and repeat that until my desired resolution. And then, since this is for dynamic collision, I delete the quadtree at the end of each iteration just to do it all over again. This is awful. Why is it so bad? God, where to begin? First off, it's bad because if we look at the divide method, each time we try to allocate a new quadtree node, the program has to exit user space to beg the computer for more memory, which is slow. From a cache locality perspective, since each allocation is unique, contiguity, while likely, is not guaranteed. Honestly, I look at the code and even though I see new and delete, in my opinion, I don't even think this code is manually managed because the locations of allocations are completely unmanaged. Christ only knows where they'll be allocated from. And finally, but most importantly for manual memory management, I can't reuse all of those unique allocations. Imagine I had additional logic before and after the broad phase collision detection. Ideally, I'd be able to use the allocation for other work I would have to do. And in the same vein, I'm going to have to update my Quadtree regularly since it's for dynamic collisions. So I'm going to have to do this whole song and dance again and again and again since I can't reuse any of those allocations. They are dead weight when I could be reusing that memory throughout the program. I'm using the memory so poorly that I have to choose between either leaking it or freeing it, which are both terrible options when I should be reusing it. Simply awful. Oh god, let me catch my breath. Okay. Whew. So, how can I do this better? Well, the solution was actually in that missile anecdote. One important technique for manual memory management is to figure out the maximum amount of memory you'll need ahead of time and just allocate that. This way, you don't have to make a bunch of slow individual allocation. Also, it ensures cache locality. Since my Quadtree class has an empty constructor, I could use an array.
No, we're not doing that.
To quote Bartleby the Scrivener, I would prefer not to. So, from here on out, it's C.
My apologies. I forgot to record these few lines. So back to the missile voiceover. So here's the code in C. As you can see, I just malloc all the memory in one go. And since I reuse the memory, I don't call free. Remember our guiding question. Why are you freeing?
And this is a rare treat I'll be recording while programming for the next part. So I'm going to iterate pretty quickly here to get the Swiss Army knife of memory management, the arena. Now, first things first, if I wanted to use this allocation for anything else in the game, like maybe say there could be more logic here. Let's say I wanted to use that Quadtree allocation for anything else. Well, first step first, what I want to do first is I want to cache the address of that allocation from malloc. And to do that, let's just hop outside of main real fast. Now I can use allocation here throughout the program, including other files. And in fact, I want to put this into the main loop, like so. Now I can reuse it again and again as long as my new data fits within the original allocation. And that leads us into the next problem. What if the data is bigger than the allocation? Easy fix, I just have to cache the capacity of the allocation so that way I can make sure I don't go over that. So going back to allocation, I would want to say in32t size cap, and then so now I'm saving the capacity of this allocation as well, so when I do allocate, I can always check that I don't go over it. And it would make more sense to do this. That is a pretty big number. What if I wanted to use it for two things? At the moment, I simply cannot, since the second value overwrites the first. How do I fix this? I just store the current size of the allocated memory. That way I can simply continue allocating and allocating while ensuring I don't go over the capacity. Now let me implement that. Now, if I wanted to use this for allocation, I would do the following. And voila, we have an arena. You really just need these three values. I'm going to use a little bit of movie magic to clean it all up since I just have some variables hanging around. So I quickly swapped in my arena struct, and as you can see, again, I have a global arena here, and I initialize my arena before the main loop. At the start of my main loop, I set the arena size equal to 0. I, of course, use Realloc, so we can go to the definition here. Super simple. This is just a method that returns the current free address of the arena while increasing the size as well. There's a cheeky little assert, so that makes sure it works. And if you note, since Realloc, I can return any size, which is how I'm able to use this again here to get the root of the quad tree, and then later on when I am initializing the new leaves of the quad tree. And that's an arena. Oh, and let me just delete that real fast. Super clean. And if I run it, works exactly the same. Now, if I wanted to use this arena for something else, there could be more logic here. Super simple. This is how I use it. I just zero out the size and I'm done. So obviously I could continue improving this with a struct of arrays instead of an array of structs. This is your reminder to read the Dod book if you haven't already, but that's a different video. Arenas will cover 95% of your memory management needs, but they have a glaringly obvious downside. Since I only track the size of allocated memory, if I decrease that number to reuse memory, all of the preceding allocations are freed whether I like it or not. This may seem like a big deal, but there are easy workarounds. If you are concerned about it, there are also a bunch of other custom allocators that are designed to address just this problem. But again, not that big of a deal. Pools are great, but they can only be used for one size. Free lists are good, but you have to over-allocate a scooch to manage each allocation individually, yada yada yada.
The creator of the Odin language, Ginger Bill, wrote a series of articles about common custom memory allocators. You can find a link to them in the description.
They're all good, except stack allocators. I've yet to encounter a scenario where I use a stack allocator instead of an arena, and I'll cover why I think stacks are just worse arenas later. But you can also just make up your own custom allocators. That's part of the fun. This might be an apocryphal story, but to make the original Fallout run on something crazy like 2 megabytes of RAM, they wrote their own custom allocator that aggressively defragmented memory to ensure they always had a large enough allocation whenever they needed it. You can also implement your own garbage collector. Really, do whatever you want to do. Malloc has and will continue to be our trusty workhorse, but what if we need more memory? We could use a second allocator, but then we'd sacrifice cache contiguity. Enter Realloc. Using Realloc, we can resize an allocation while keeping all the data already in it. Now, this sounds great, but there is an important catch. If we look at this straightforward code right here, I allocate 6 bytes for my pleasant
hello,
and then I just realloc up to a properly big number. But the second time I print, it's garbage. And this is the catch. While Realloc does copy the data in the allocation, unfortunately, it is not guaranteed to return an allocation with the same address as the original. Now, since Realloc frees the original pointer if it does return a new address, any pointers to the old allocation are now dangling. And if you use them, you cause a use after free bug, which is what happened during the second print. So, what's the workaround for this? Relative pointers. And this is the point where I gotta have a heart-to-heart with you. If you're afraid of pointer arithmetic, you have to grow a pair. Relative pointers only work because of pointer arithmetic. You may protest. It's unsafe. You could write to anywhere. Coward. Can you even call your deracinated existence a life? Go ahead, hit me with that thumbs down. You know I'm right. So, relative pointers are pretty straightforward. A pointer is just the value of an address in memory, which is just a number. So instead of storing the entire address, a relative pointer is just the difference from one address to another. There are 2 types of relative pointers that solve the Realloc problem: offset pointers and self-relative pointers. As you can probably guess by the names, offset pointers store the difference from some base pointer to another pointer, whereas self-relative pointers store the relative difference from its own address. I wrote a simple, relatively linked list of integers to demonstrate how to use them and how I can freely realloc the linked list allocation. And yes, relative pointers do have a bit of mental overhead, but they offer a number of benefits beyond reallocation. First off, Relative pointers can be smaller than actual pointers. Looking at my linked list implementation, I use regular 4-byte integers instead of the whole 8 bytes for addresses because I know my linked list is going to stay smaller than 2 terabytes. Relative pointers also allow you to copy and serialize heap data in one line. Let me say that again. Copy and serialize heap data in one line. Look at the code. I don't write clone functions. I just memcopy. I don't write serializing functions. I just memcopy. All of that is trivial with relative pointers. Like, if you know, you know. This is huge. You can also get most of the advantages of relative pointers if you use indices into arrays. If you want to read more about relative pointers, Ginger Bill also wrote a great article covering them. He also includes videos covering relative pointers by Sergey Migdalsky, a Valve engineer, and John Blow, most notable for not sending me my Jai beta key yet. John! I found Sergey's talk especially interesting because he covers how they use a single big allocation and relative pointers to manage all of Half-Life 2's physics items, and that lets them support quick saving by, you guessed it, just memcopying. The links to Ginger Bill's article and the 2 videos are also in the description. Now, while Malloc and Realloc will always be the 1-2 special, I would be remiss not to cover Calloc and Alloca as well. Calloc lets you zero out your allocations. Unfortunately, Calloc assumes you are using it to clear an array, so it takes the number and size of each element, which is kinda weird. Or you could just use Malloc and then use memset to zero it out yourself. And we also have Alloca. Alloca is exactly like Malloc, but instead of allocating memory on the heap, it allocates memory on the stack instead. This means it frees itself once the variable exits the stack frame. So at the end of the day, if you ever need a quick hit of memory and you're not worried about causing a stack overflow, Alloca works perfectly fine. There's also memory mapping, which is super powerful, but it is platform specific, so I can't be bothered to cover it here. Check the source code of the repo if you want to see how to do it on Windows and Linux. Finally, the second question of manual memory management is, when should you reuse data? And unfortunately, this is the part where I am actually forgetting where I learned this. I'm just so deep in programming blogs that I forget the provenance of some of the stuff I learned.
It turns out Ginger Bill writes about lifetimes in his Memory Allocation Strategies series, but I read about them elsewhere, which is why I use different terms. Unfortunately, I still don't remember where.
But when you do start managing your memory, especially if you use an arena, you'll see that data can be organized into groups that have similar lifetimes. On one end, you have stuff that you only need for a little bit. This is scratch data. And on the opposite end, you have data you need the entire runtime. This is static data. And in the middle, we have working data. So going back to the Quadtree example, since I only use the Quadtree during dynamic collision checks, I would say it falls under working data. This is sort of a personal taste thing, but it makes sense to me to use different allocators, both individually unique and different types, for different lifetimes. Arenas seem the perfect fit for scratch data, whereas static data depends more on the data structure itself. Free lists are good for trees, pools are great too, and if you just want an array, there's really no reason to not use Malloc. And this is why I think stacked allocators are secretly bad arenas. Since arenas only offer rough-grained control over allocations, the quick, brain-off way to manage arena allocations is to just set the arena size back to 0 in order to return all of the allocated data. This naturally encourages you to think in lifetimes for groups of allocations, since you are looking for the point where you can just grug brain zero the size. Whereas stack allocators offer a damning amount of control over individual allocations. Compared to pools and free lists, you can't free your allocations in whatever order you please. It's a stack, so you have to free things in a first in, last out order. So instead of thinking of data in groups, you're instead wasting your time worrying about individual allocations. Maybe this makes sense for embedded systems, I simply do not know. But this strikes me as antithetical to proficient memory management. So, I am 100% out of prescriptive advice, and now it's simply taste. How do I manage memory? I basically use an arena pool. Yes, you heard me right. I use a pool of arenas for all of my non-static memory, and for my static memory, I mostly use Malloc since I make a lot of tables. Yes, I could use a free list for my scratch allocations, but I find the arena pool easier to use since I can always allocate more without having to use relative pointers all of the time. And this check and all function makes managing my scratch arenas super easy, since at the end of each iteration of my main loop, I know the data in my scratch arenas is not being used. So even if I forget to clear an individual arena, I can manage the whole group with one simple function. And this is not my area of expertise at all, but it does seem that using custom allocators well makes memory safety easier. Yes, I can still use after free, but since I think in lifetimes, I deallocate a bunch of stuff all in one go instead of aggressively freeing to prevent memory leaks. I can still buffer overflow, but again, going back to the missile anecdote, I try to figure out how much memory I need first with some additional overhead.
I also use fat pointers or slices for bounds checking.
So that ends up not really happening as well. And finally, memory leaks, though not under the umbrella of memory safety, are just impossible with my scratch allocator since I track all of my scratch arenas, so that memory is by definition never leaked. Now finally, and this is the real next level stuff, allocation failure becomes optional. If you want to make your program keep running even though your allocators are topped off, you can just return a trash buffer instead of something from the allocator itself, and then seamlessly recover while continuing to run. I don't personally do this, but I can if I need to, and that's because I'm actually managing my memory. But we all know just watching a goofy video on YouTube is no substitute for putting in the hours. So here's the secret to improving: Malloc Golf. Without allocating everything on the stack, write a program that minimizes the times you call malloc. Try to call malloc once. It doesn't have to be a big, impressive program. Small is good. If you can't think of something, I suggest writing a simple, terminal-based tic-tac-toe game without recursion and an AI opponent. Don't use Alloca and have fun. And that is that. Important note, I did not talk about data alignment, but I think this comment I pinned on the ECS video really demonstrates the advantages of it. It's better for the cache and it's better for SIMD. So that should be more than enough incentive for you to check it out independently at this point. If you look at my source code, I have an aligned arena allocator function. Also, tag pointers. Hilarious idea, but unfortunately, I haven't found the excuse to use them yet. Also, God, I mentioned Ginger Bill so many times in this episode alone. I reference his articles every episode at this point. They're just that good. I gotta say, of all the C successors that have popped up within the last decade, Odin looks the best. I really ought to send Bill a bottle of champagne or some nice cigars at this point. Okay, this is the real end, I swear. Thank you for watching, I appreciate your time, and I hope you have a good day. If you liked the video, please give it a like. And if you're interested in my next video, please subscribe. Please leave a comment. As I said at the start, that's why I made this video. And aside from everything else mentioned in this video, there's a link to the Discord server for this channel, where you can also make more suggestions. There's a programming channel where feel free to turn in your Malloc golf assignments. And it's not all just homework, there's also a cooking and baking channel where you are more than welcome to post things you cooked or baked recently. And speaking of baking, let's get to it. Alright, look at this little thing. This is something I do just occasionally. I usually don't take pictures of it when I do, but when I do make loaves, sometimes I'll just pinch off a little bit and I'll make a little bun that I have with my dinner that evening. And so as we can see, this is just a little sourdough bun, or excuse me, yeah, a little, it's not even sour because, you know, it's just, didn't really ferment that long. But if we take a look inside, nice. You can't really, unfortunately, it does rise well. Unfortunately, you don't get a great picture of the crumb, but you know, it's good. It's good. And it's pretty tight. It's got a good rise there. I'm surprised. Yeah, it rose pretty well. I didn't get much of an ear, unfortunately, but you know, it's just a little bun, just for fun. A fun bun, one might say. But if we look at the actual loads, and let me see if there are any notes. Nope, no notes. Well, whatever. Looking at the loaves, 2 gorgeous loaves. Not that good of an ear. I think, you know, I'm trying to figure. This is something I haven't really figured out still. I don't get reliable, like real good ears, and I don't know. I think part of it is I'm not tensioning the bread enough. Other times I think I'm just cutting too deep. Like maybe I need to cut less so that way, just the bread kind of just throughs the cut. I don't know. And I'm still experimenting. I'm still learning. Even though I mostly go for the cross slash now, just because, since I do make a boule, I do find that the cross, it's a more even crumb, whereas a single slash on the boule, it's a little less even. Because, speaking of this cross section, well, even though I said that if looking at this cross section here, it looks gorgeous nonetheless, looks pretty uniform. But I mean, even looking at it, you can see there's kind of whoops to the cut. And not much. I'm zooming in right now, so that's why I'm physically leaned in while I zoom in, but still not much in a veneer. And I mean, looking at this, I will admit, this looks, I want to say this is 75%. I was probably taking it easy on this one. So it wouldn't be too surprising if I didn't get that much oven spring. But I mean, that's perfectly fine. And I will say the real low, like if I start to go beyond 80 and 85% hydration, like it's just, sometimes it's too airy, like if I want a bread that I can just smear butter on, oh my god, I don't want like the 85% hydration bread, because it's like half of it is just holes, and I got like butter dripping onto my hands. I was like, oh, it's a mess, and now I'm like slurping the butter off my fingers. It's a mess. Whereas I mean, that's good if I want to like put some cheese on it with some meats, some nice gabagool, which is capicola for you non-Guido Americans. But yeah, so that's why sometimes I drop it down to 75%. Sometimes I'm like, what am I going to use this bread for? And also sometimes if I'm like giving it away as a gift, I'm like, you know what, Mr. XYZ, if Mr. XYZ of the XYZ affair, he doesn't strike me as someone that wants real artisanal bread. And because, that's perfectly fine. Like, sometimes I just expect people to make just sandwiches with the bread. And I don't want them having the same problem as me. Well, if they're trying to make a peanut butter and jelly sandwich, they got jelly dripping on their hands. That's a no-go. That's a no-go. But anyways, so that's my hydration decision-making process. It's like, what do I want? What do I think other people want? Other times I know people who are real into bread. I hit them with a high hydration. I gave them a brunette, high hydration brunette. I'm always a brunette kind of guy. I like a nice brown on my loaves. But, as I said, I vary. Sometimes I like higher hydration. Other times I like a nice, good, dependable 75%. It's whatever strikes. It's whatever mood I'm in. But anyways, I think I can use these. Yeah, no guilt. Again, I'm having a good run, guilt-free sign-offs. Yes, the yeast in the air is free, so go out there and bake. It's nutritious, it's delicious, it's good for you, and it makes a great gift. And it's a great way to show people that you appreciate them, and I appreciate all of you. So thank you for watching, and I will see you next time.